Hello, this is Professor Kernler, and in this next video we're going to talk about section 17.7, Stokes Theorem. What we've been working toward in the last couple of sections is getting to three dimensions. We had Green's theorem focused on two dimensions where the line integral was equal to the integral, double integral over the area, whether it's curl or divergence, depending on whether you were looking for the circulation or the flux. And so now we're looking at three-dimensional versions of that. We had this new surface integral idea in the previous section, and so this is going to be an application of that. So let's refresh our memory of Green's theorem, the circulation form. We have some region, it's a connected region, we have an oriented curve around it, the line integral along the curve will be equal to the double integral of the curl. So that's the Green's theorem. So Stokes' theorem is going to be a three-dimensional version of this. There are some tweaks to it here. So you still have a curve, and it's an oriented curve, right? But now you're in three dimensions. And then you have a surface instead of a region. And so what you would do is instead of finding the integral, there's two options here, right? You can have the line integral along the curve, or you can find the surface integral. There are a couple of additional layers of complexity to this, like requirements for this theorem to hold. First of all, the surface must be oriented. So it must be an orientable surface, and the orientation has to be consistent between the boundary, the curve C, and the surface. What that means is you use what we would call the right-hand rule. And so for this particular visual that I have here, this one would have to be oriented outward because the curve, if you follow it with your right-hand rule, the thumb points in the direction of the orientation where the normal vectors are to this particular surface. So that's the orientation. It's oriented outward, and that we use the right-hand rule to make sure that our curve matches that orientation. This is going to be relevant. We'll see this right away in the first example. So what Stokes' theorem says is that the line integral of the field dot dr, so the circulation, is equal to the double integral, the surface integral, of the curl, so that's the gradient operator, cross product with the field, dot n ds. And you'll often see this noted, that's the surface integral. You often see this notation as just curl of f dot with ds, just the notation for that. Okay, so let's try an example. Wait, no, we have to talk about our silly little comic over here. So the idea here with this, obviously, like we're getting pretty complex here. This is Calc 3. We're not messing around anymore. So what Stokes' theorem is if you want to know how much, this is the curl, how much swirl there is in there, well, what you can do is draw a curve around it and find the circulation on the curve, and that will tell you how much swirl there is inside of it. That's the idea behind the comic. Get my recording window lined up here. All right, so let's try this first example. We're going to try to verify that Stokes' theorem is true for this particular field and the surface S here, which is the unit hemisphere, but we're only looking at negative x values. So let's see here. We're going to need a curve, and so we're going to need to curve around here, and I'm drawing it actually in the orientation we want. That's the orientation our curve is going to have to be because of that right-hand rule. If we look at the hemisphere is oriented outward. Notice it has the normal vector drawn outward, so we need our thumb of our right hand as we follow the curve around. We need our thumb to be in the direction of outward from that hemisphere. Okay, so with that in mind, let's take a look at that curve. It's in the YZ plane, so we can look at just the YZ plane. It's the unit hemisphere, so this is basically the unit circle. It's in the YZ plane, so we know x is 0. So for our curve, we definitely know x is 0. And you might be tempted to say, well, let's just go cosine t sine t in the unit circle. Makes sense, right? The problem with that is the unit circle has a counterclockwise orientation, right? That has this orientation. So, and that would be the opposite of what we need. So we need to switch that. So all we can do, or not all we can do, but one thing we could do is actually just switch the x and y. And now that'll of course will start up, or not the x and y, the y and z. It'll start up at 1 and then have the orientation where it'll rotate in the direction that we want. Okay, let's see. We want to do the line integral. So let's look at, on that particular curve, what does our field look like? Well, it's the opposite of z, so it's negative cosine t, and then it's x, that's 0, and then 0. Well, that's convenient. Nice simple field on the curve at least. So we would do the line integral f dot dr, and that would be the integral over the curve. Our field becomes negative cosine t 0, 0, and then dot product with dr, which of course would be r prime dt. That's 0 cosine t negative sine t dt. Well, that's pretty sweet. That's just the line integral. I mean, I guess we could put our 0 to 2 pi. I never did my interval for t here, did I? We need to specify that t goes from 0 to 2 pi. That gives us 1 revolution around that curve. So this is the integral from 0 to 2 pi of 0 dt, which is just 0. So apparently there is no swirly inside this one. So the circulation, there's no circulation, no net circulation on that curve, and there's no net curl inside either. So this one is the easy one for this particular example. So let's try the other one where we're going to have to do the surface integral. So this is going to be the surface integral of the curl of f dot ds. Okay, so this is going to be double integral over the region R of our curl of f dot product with, if you look back on, I'm trying to think of what section this is in, I'm trying to think what page it's in. It's in 17.6, surface integrals. This is where we parameterize our surface. And we need to get the curl of f. We'll need to get that in terms of our parameters eventually. But we need to parameterize our surface and find these two unit vectors. This is a hemisphere. So again, we can refer to example 5 from section 17.6 again. We can use the parameterization. Got it written down here. Sine u cosine v. There's normally a radius in front of that, but our radius is 1. Sine u cosine v, and then sine u sine v, and then cosine u. And let's see here. We need to do just, that's for the whole sphere. U is phi, and v is theta. So we actually need phi to go all the way around because we need to have the top and the bottom in terms of z. So we need u to go from 0 to pi. But then v, we don't want to go all the way around the xy plane. We just want from pi over 2 to 3 pi over 2. Okay, again from example 15, we have the cross product. This would be a tedious one to compute again, so I'm just going to write it down here. It is sine squared u cosine v, sine squared u sine v, and then cosine u sine u. That was from our 17.6 example 5. Where did that one go? All right, so we have it right here in the middle of that one. Okay, so back to ours. Now we need to find, so that's that. We need to find the curl. Whoops. Which will be the gradient operator cross product with our field. That'll be j, k. And that's the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And our field was, actually I don't think I needed this much space, right? Negative z, x, 0. That'll be, let's see here, I times, we'll have, we're going here, partial derivative of 0 with respect to y, minus partial derivative of x with respect to z, that's 0, minus j times, that'll be here, 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 a little sloppy there, but partial derivative of 0 with respect to x, that's 0, minus the partial derivative of z with respect to, or negative z, so that'll be minus negative 1, so that'll end up being plus 1, plus k times, and then that'll be here, so partial derivative of x with respect to x, minus the partial derivative of negative z with respect to y, which is 0. So we get 0, negative 1, 1. All right, that's our curl. At least the curl is simple here. Okay, we need to then go, let's see, we'll call this star. Now down here, star equals double integral over the region, that's going to be in UV. Curl of f is 0, 1, negative 1. Dot product with sine squared u cosine v, sine squared u sine v, and cosine u sine u. And that'll be dA. All right, and then when we do our dot product, we will get negative sine squared u sine v. That's a negative 1 times sine squared u sine v, and then plus cosine u sine u. And then, boy, we can do du dv, dv du. I think I'd rather do v first because I'm kind of hoping I don't have to do a power reducing identity for the sine squared u. So v goes from pi over 2 to 3 pi over 2, and u goes from 0 to pi. All right, so let's see here. This would be, actually this would be end up being positive, right? Sine squared u times cosine v plus, and then just cosine u sine u times v from pi over 2 to 3 pi over 2, then that's du. Alright, so that's 0 to pi. We'll have sine squared, this is going to be a little clunky here, sine squared u cosine of 3 pi over 2 plus cosine of u sine of u times 3 pi over 2 minus sine squared u cosine of pi over 2 plus cosine of u sine of u times pi over 2 du. Whew. All right, well, conveniently, cosine of 3 pi over 2 and cosine of pi over 2 are 0. So we're left with the integral from 0 to pi, and then we'll have 3 pi over 2 minus pi over 2 of those, so that'll be pi times cosine of u sine of u du. Here we can do a substitution like w equals sine of u, dw equals cosine of u du, so that's perfect. And then w at 0 equals sine of 0, which is 0. Oh, and then w at pi equals 0. So this is actually just pi times the integral from 0 to 0 of u, or w dw. So that's just 0. But of course, we already knew it was going to be 0 because we did the much simpler line integral up above. We already knew this was going to be 0. So the point of this problem is we were just going to practice verifying that Stokes' theorem was true. Okay, we've got a couple more here. Next one looks worse because look at this surface, and you're not even really like given any information about the surface. Just calculate the surface integral, the curl of the field over that surface, and I'm given the field. It's z 2xy, x plus y. The surface is oriented outward. And so then you're thinking like, hold on, this is some crazy worm surface. I must need to use Stokes Theorem. And so the key is that curve there. I feel like I need a bright color, like a red or something here. This curve. Now I need to orient it clockwise there because I need my thumb to point outward on this surface. So all we're going to do is find the line integral along that curve. And let's see here, x, z, it's up 1 for some reason. This is 2. So it's not quite like a unit circle because the z value has been shifted up 1. So that's pretty manageable actually. The y value is 0. And we need to, what's the orientation on there? Let's see, x. Ooh, this is kind of weird. Because I drew it opposite of the way it is over here, right? This is positive x, so it's going up there. So it, ooh, that's confusing. In fact, that's different from what I did when I prepared this. But that's what it is when x is positive. As x increases, z is increasing in order to get that right-hand rule. As x increases, z increases. So that's the orientation. So let's see here. This means we want basically the unit circle, but the z should be shifted up 1. So we'll do cosine t and 1 plus sine t. We want to do all the way around, so t would go from 0 to 2 pi. Okay, on that curve, our force, or I keep saying force, our field would be, all right, the field is z, 1 plus sine t. Let me actually just go over this way. So the field is 1 plus sine t, and then it's 2xy, so that's 0. And then it's x plus y, so that's cosine t. Nice. All right, and then let's see, what else do we need? We need, I think we're ready to do the line integral here. All right, that'll be 0 to 2 pi. My field became 1 plus sine t, 0 cosine t, dot product with r prime, negative sine t, 0 cosine t, dt. And let's see here, we multiply the x values there, and then multiply the y's, that's 0, multiply the z's, that'll be cosine squared dt. Ooh, you know what? That's a trig identity. Cosine squared minus sine squared is cosine of 2t. So this will be the integral from 0 to 2 pi of negative sine t plus cosine of 2t. Excellent. So that's cosine of t plus 1/2 sine of 2t from 0 to 2 pi. Oh, cosine of 2 pi plus 1/2 sine of 2 pi minus cosine of 0, which is the same as cosine of 2 pi, plus 1/2 sine of 0. And that was a lot of work to get another 0. All right. One last example, just to show the benefit. That one, we did one where we verified that it was true and we showed both. Then we did one where the line integral was easier. So let's do one where the surface integral. Just do the surface integral. Okay, we're going to evaluate the line integral over this field. C consists of 3 line segments that bound this plane in the first octant. Ooh, okay, so first octant, it looks like we have not much x, a little bit of y, but more z. So 2 on the x, 4 on the y, 8 on the z. And you can check that if you substitute like 0 for x and y, you see it intersects the z-axis at 8, etc. Okay, so we are going from 008 to 200, then to 040, then back to 008. That's our circulation. So the circulation, and if we follow that path, the surface would be oriented upward. Okay, so that's good. And here is our surface. So if we were going to do a line integral, we'd actually have to do 3 of them. 3 line integrals. We're going to try the surface integral instead. So that line integral, we're going to do the surface integral instead of the curl of f dot ds. This particular case, the z is given to us explicitly as a function of x and y. And so, we can find the double integral over the region, and then we have this, I believe it's from page 169 in section 17.6, that this is negative partial derivative of z with respect to x, negative partial derivative of z with respect to y, 1 dA. And that's in the xy plane. No need to parameterize if your surface is a function of x and y. Basically, you're parameterizing it with u equals x and v equals y, and so you can get this form, and that's back in the surface integral section. Okay, we need to get that curl of f. That's I, j, k. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And we have z, negative z, x squared minus y squared. Okay, so that's I times, and then we'll go this way, partial derivative with respect to y, negative 2y, minus partial derivative with respect to z, which would be negative 1, so that'll end up being plus 1, minus j, times, and that'll be here to here to here to here. Partial derivative with respect to x, 2x, minus partial derivative with respect to z, 1. And then plus k times, and that'll be here, partial derivative with respect to x, that's 0, minus partial derivative with respect to y, 0. Okay, not too bad. Could be worse. Negative 2y plus 1. Negative 2x plus 1, right, distributing the negative in there, and then 0. Okay, so the curl of f dot product with our negative zx, negative zy1 will be equal to negative 2y plus 1, negative 2x plus 1, 0, dot product with, where's my z? 8 minus 4x minus 2y. The partial derivative of z with respect to x will be negative 4, and the partial derivative of z with respect to y will be negative 2. But we want the opposites of those, so that'll be 4, 2, 1. Okay, so that's negative 8y plus 4 minus 4x plus 2, and then plus 0. So it looks like negative 8y minus 4x plus 6. So that is what we are going to integrate over the region. Okay. So the surface integral of the curl of f dot ds becomes double integral of negative 8y minus 4x plus 6 over the region. I think I need to do this in a different color. So the region here is the region in the xy plane. Let's maybe, how about we go over to the left to do that. X, 2, y, 4. So that'll be y equals negative 2x plus 4. So we could integrate y from 0 to negative 2x plus 4, and then x from 0 to 2. We'll go dy dx, y goes from 0 to negative 2x plus 4, x goes from 0 to 2. And at that point, I mean, we did a lot of work to get here. Maybe the 3-line integrals would have been easier, but that would be pretty tedious, finding all those cross products and all that. So from here, this is a relatively simple double integral. I have the answer written down here. It is negative 88 thirds. Okay, so that is it for Stokes' theorem. The big idea, again, the big idea is the theorem itself. If you want to find how much curl, the net curl there is inside, you can do a line integral and get the circulation of a curve that kind of encloses that surface that's at the boundary of the surface, as long as the orientation of the curve is consistent with the orientation of the surface.